This is part one of a two-part lesson on entropy. So entropy, we designate it by the capital letter S, and it is a measure of the disorder of a system. Another way to explain it. And the greater the disorder of a system, the greater the entropy. So entropy is something that you have. Like you have energy, everything has entropy. And the more spread out the energy is, the greater the disorder or the entropy is. And the more freedom of motion the particles have, the greater the entropy of the system is. And the more microstates, the greater the entropy. So if you have a gas and you took a picture of it, that would be a microstate. Take a picture a few seconds later, that would be another microstate. So the more microstates, the greater the entropy. So the third law of thermodynamics says that the entropy of a perfect crystal at 0 Kelvin is 0. Anything that has a temperature above 0 has some entropy S. So we know that temperature is proportional to kinetic energy. That's what temperature is. It's a measure of the kinetic energy. Our formula for kinetic energy is 1/2 the mass times the velocity squared. So this is saying that if you have a temperature of 0 for your perfect crystal, then the mass would not be 0. That means that your velocity will have to be 0. So at 0 Kelvin, there is no movement. And this is a perfect state. When matter gets close to 0 Kelvin, it starts behaving strangely compared to how we're used to dealing with matter, and it kind of turns into a matter goo. So you can't have a perfect crystal at 0 Kelvin. That would be an ideal state. So here we have our perfect crystal. So we have some kind of polar compound where we have a delta plus at one end and a delta minus at the other end. And so in the solid state, our particles arrange themselves so that the plus of one is facing the minus of the other. So here's our perfect crystal. Now, in reality, when you have crystals, you can have irregularities in the crystal structure. So you might have a missing spot, or you can have a molecule that's not perfectly aligned. And in our state where we're not at 0 Kelvin, we have vibrations happening. Here, our particles will be perfectly still, but when we have a temperature, our particles vibrate. Okay, so the units of entropy are joules per Kelvin times moles. We're not going to be doing any of the mathematics today. We'll be doing that in part 2. So what we're interested in, aside from the entropy, is the change in entropy, the delta S of a system. So our delta S is positive if we're going from a less ordered to a more disordered state. Or the converse of that, our delta S is negative if we're going from a more ordered to a less disordered state. So we can look at it in terms of how we're getting more or less ordered or how we're getting more or less disordered. But I just think of entropy as disorder. So when you're getting more disordered, it's positive. Okay, so we're going to look at the different entropy changes so we can predict the sign, S-I-G-N, of delta S for different types of changes. So here we see a phase change. So here we have a solid where all of our particles are in the crystal lattice structure, organized, rigid. They cannot move past one another. Although if there's a temperature, then of course they would be vibrating back and forth. So if we heat up our solid, we will get a liquid. So here our particles are moving. They have rotational movement as well as translational movement. So now we can see that going from a solid to a liquid, our delta S would be positive. We have a positive delta S. We're getting more disordered. And then when we go from the liquid to the gas, now our particles are more spread out. Now we have even greater disorder. So the delta S going from liquid to gas is also positive. And the biggest change in entropy comes from going from a liquid to a gas. Then if we went the other way, if we went from a gas to a liquid, now we're getting more ordered or less disordered. This would have a negative delta S. And going from a liquid to a solid, getting more ordered or less disordered, we would also have a negative delta S. So my suggestion is just to learn it one way. If you can understand it this way, then if you have the opposite situation, just do it this way and flip it. Okay, so that's our most important factor for delta S. We can also look at the delta S for volume changes. So here we have our gas all spread out, and here we've pushed the plunger down, the piston down, and now our gas particles are closer together. Well, there's many more states of where these particles can be here than there are here. So here we have a higher entropy because we're more spread out. If our energy is spread out, our entropy is higher. So here we have a higher entropy. And here we have a lower entropy. So our change going from higher to lower means that we have a negative delta S because we're getting more ordered or less disordered. So going the other way, if we increase the volume, then we would have a positive delta S, or entropy. For temperature changes, if we increase the temperature, then we increase the kinetic energy, and we have more energy states, so our entropy would increase. So if temperature increases, kinetic energy increases, and entropy increases. So our delta S would be positive for increasing the temperature and negative for decreasing the temperature. So positive delta S for increasing temperature, negative delta S for the opposite. Number of moles change. If we go from less moles to more moles, we get more disorder, more entropy. So you can think of this as, think of items in your room. If you have 5 items in your room, and then think of having 100 items in your room, you can create a lot more disorder throwing those 100 items around than you can if you just throw your 5 items around. So the more particles we have, the more entropy we have. So if number of moles goes up, entropy goes up. So our delta S is positive with an increase in the number of moles. Same with molar mass. Our entropy increases with increasing molar mass because we have more electrons that can be in different energy levels. So the energy can be, there's more microstates. So as molar mass increases, our entropy increases. So delta S would increase for increased molar mass. And then as molecular complexity changes, that is the number of bonds, then entropy changes as well. And the trend is the more bonds there are, the greater the molecular complexity and the greater the entropy. So let's look at something with 0 bonds, as in helium or argon, one of our noble gases. So this particle can rotate and it can translate, but it can't vibrate because it doesn't have anything to vibrate with. If we have one bond, it can also rotate. The molecule can rotate and it can translate, but it can also vibrate. So our bond can stretch out and then go back in. So this can go back and forth. This is called a symmetrical stretch. And it turns out that these stretches are quantum. So if the right photon hits our molecule, the stretching will get larger. It'll vibrate back and forth with a longer distance between the particles. So our particles can go back and forth. Okay, now let's look at two bonds. Now we're going to get a lot of different types of vibrations that we can have. So we can have the symmetrical stretch. So there's our one molecule with our other. Let's make this so we can really, the bonds can stretch out and then the bonds can shorten. So we're going from one state to the other with the energy it has, long stretch to short stretch. So we have our symmetrical stretch. But we can also have an asymmetrical stretch. So one side can stretch out and the other side contract in. And then that changes sides. Then we have our other side that stretches out and the first side can stretch back in. So we have a stretch going like that. So this is asymmetrical. Stretch. With our bond, so we have a bond angle here. So in water, that would be 104.5. Well, our bonds can move up and down. That angle can change. So we can go from this to this back and forth. So we're going up and down that way. And so this is called bending. And then we could also have these two go in and out of the plane, and I believe that's called wagging. So there's a lot of different things, a lot of different vibrational states that you can have with two bonds. And if we go to 3 and 4 and 5 bonds, then we can have even more different types of bond vibrations going on. And this is a big reason why we have the greenhouse gases. I'm not going to go into all that, but any molecule with 2 or more, 3 or more atoms contributes to global warming, greenhouse gases. Okay, so we are going to now predict the sign of delta S for different processes, and they can be chemical processes or physical processes. So here we have a chemical reaction, and we want to figure out, is the entropy of the system increasing, a positive delta S, or is the entropy of the system decreasing, a negative delta S? So we check our states of matter. Always check that first, because that's the most important thing. So we have a solid and a gas going to just a solid. So the fact that this gas is ending up in the solid means we are getting more ordered or less disordered. It means our entropy is going down. So we have a negative delta S for that process. Okay, let's look at another example. Let's look at when we have sodium chloride. And we put that in water. And we get sodium ions and chloride ions. So here we have sodium chloride in a crystal lattice of alternating positive and negative ions. Here we have ions that are free to move throughout the water solution. So what has more disorder? Are particles all in a rigid structure where they can't move past one another, or are ions that are freely moving about in the solution? So here the disorder is increasing. We have a positive delta S. All right, let's look at this example. The synthesis of ammonia. So we have nitrogen gas and hydrogen gas making ammonia gas. And we want to figure out the delta S. So here we have gas, gas, gas. So we need to consider the moles that we have. So here we have 1 mole of nitrogen and 3 moles of hydrogen. So we have 4 moles of gas particles that go to 2 moles of gas particles. So the entropy is decreasing. Think of your room. It can be a lot messier when you have more stuff in it than it can be when you have less stuff in it. So our entropy is going down. We have a negative delta S. Okay, our next example. Iodine solid goes to iodine gas. So when we have a substance that goes from a solid directly to a gas, that is called sublimation. Here we're in an ordered crystal lattice. Here we have our iodine molecules freely expanding into whatever volume we have. So of course this is a positive delta S. A gas has much more entropy than a solid. Okay, let's look at another one. So we have CaCO3, calcium carbonate solid. You heat that up and you get calcium oxide solid and CO2. Wait a minute, something's wrong. Why do I have CO2? Oh yeah, CO2 gas. So we have a solid and it's producing a gas. So a gas has much more entropy. So this also has a positive delta S. And then our last example, if we have some water vapor and it condenses into liquid water, right, a condensation, phase change. Well, here our gas has a whole lot of entropy. The liquid has less entropy, so we have a negative delta S. All right, so you should be able to qualitatively determine the sign of the delta S, and then tomorrow we'll do equations and calculate delta S for different processes. That's it.